Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Here's today I will show my demonstration video for final year project. I will be use MATLAB-Simulink for final year project. My title is closed loop boost converter with SPWM inverter. So for refreshings, at the last final year project, I will be discussing the open loop system, which is a boost converter, and the SPWM inverter. The boost converter itself will constrain the output voltage and inject it to the SPWM inverter to see the total harmonic distortion that should be below than 5%. And for my final year project too, I will be focused on boost converter itself to have a closed loop system, which when I'm varying their input from 24 volt rangely change to 21 volts in between them, and we have a constant output at 50 volt before injecting direct to the SPWM inverter. By varying to understanding the characteristic of the boost converter, firstly I will have to the transfer function of these systems, which I have learned in modeling of power electronic. So here I have the continuous time transfer functions where I have been calculated with all parameter that I be used in the boost converter. And then in this part I will use the single input and single output design tools, which short form is Jusoh, to get their transfer functions to see their dot plot. So here is the dot plot for my uncompensated boost converter, which it shows that this system is unstable loop with a gain margin of minus 37.5 dB and a phase margin at minus 159 degree, and of course the cost over frequency is at 4.63 to the power of 4 radian per second. By tune these uncompensated systems, I'll be used the PID tuning, and of course I can change the phase margin and the bandwidth as I desire, and then it will come up with equation for my PID systems that will be inserted in the PID block in Simulink later. So I just update the capacitor. Okay, here's come the compensated of my boost converter. This comes the equation for my PID systems, and this system is at stable loop with a phase margin of 94.6 degree, and the frequency is at 211, the bandwidth frequency. And we can see at the right here is the step response of the systems. The step response is rarely be changed if I changing the gains and having the phase margin at, let's say, 60 to XT, rarely change. The step response will show the increasing of the overshoot and settling time if I have a phase margin lower at 60 degree, and it will be lesser if I gain the phase margins by increasing the gain at the magnitude dot plot. So then after I creating doing this PID tuning at control system designs, the next phase is I will be injected the equation just now into my PID block. So here's come is my subsystem for the boost converter. So then by applying that, I will have the input of my subsystem and output of boost converter, and of course the output of PWM signal will be injected directly to the switching device. Later then we can see. So here I'll be running my simulations. At the input from 24 volt, I will be running to decrease a little bit at 21 volt, and then we can see at the output of the voltage and the current cell for this boost converter, there will be a ripple or a ringing effect before it becomes stable later. But at this stage, before it becomes constant, it will have a ringing effect. This will be contribute to how fast my feedback system react to the output of my boost converter. This part I will be discussing more in my writing or in my thesis paper. So at the last part, after getting the constant output of 50 volt and 5 amp at my boost converter, and then I will be inject directly to my SPWM inverter to see how the THD, total harmonic distortion, will form because of this system. It should be lower than 5% according to the IEEE standard. So here's a simulation for my voltage and current output inverter. The top one is the output voltage and the bottom one is the current voltage. It shows that it will form a smooth AC waveform, and at the 0.1 second here, when my input 24 volt will be changed to 21 volt, is really not have significant changing in the output of the inverter, and it shows that this inverter is having the output of AC waveform in the good conditions. So to see the total harmonic distortion, I will use the FFT analysis, and this analysis shows the total harmonic distortion at the particular AC waveform that just shows in SPWM inverter output. Be taken from 0.02 seconds, 5 number of cycles at 50 Hz, and we can see the total harmonic distortion is at 4.65%, which is below than 5%, and the fundamental of this output is really at 52.7 volts. It shows that this total harmonic distortion is below than 5%, and it will be good result. So I think that's all for my demonstration review. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.